Hi everyone, my name is Samia, and our paper is called Auditing for Gerrymandering by Identifying Disenfranchised Individuals. We study the problem of computationally auditing a map for evidence of gerrymandering. So, what is gerrymandering? It is defined as the practice of drawing congressional districts, such as to favor or disadvantage particular population groups or electoral outcomes. So here, for example, I have a state with 50 people, and let's say I want to divide the state into 5 districts. So under the constraint that each of the districts have roughly the same population as that of others, we can come up with 3 possible maps as shown here. So in the first map, we have the outcome that the blue party wins 3 districts, whereas the red party wins 2. This is actually fully representative of the distribution of voters in the original state, where we also have a party support of 3:2. In the second map, we have one of the most intuitive map designs, but that which leads to a surprising outcome, that all 5 of the seats reserved for the state has been won by the blue party, even though 40% of the voters are actually in favor of the red party. And last but not least, in the third map, we see another surprising outcome where just with 40%, the red party is actually still able to win majority of the seats of the state. How does this happen? If we zoom in a little bit closer on this third map, we see that in the 2 districts where the blue party does win, they win with a supermajority of 90%. So this is implying that by packing or over concentrating the blue voters into certain districts, you are able to dilute their voting power in other districts, and so tip the balance in favor of the red party. So with that, we have a little bit of understanding of what might be an instance of an unfair or gerrymandered districting. But unfortunately, there is no single gold standard to identifying and quantifying instance of gerrymandering. So a number of metrics exist in the literature to identify and quantify gerrymandering. For example, proportionality that we saw map 1 was able to perfectly retain. Efficiency gap, which counts the difference between 2 parties' wasted votes divided by the total number of votes cast, where wasted refers to votes that are cast in excess of a majority or those that are cast for a losing party. MCMC methods, which analyze the likelihood of the outcome of a given state map compared to outcomes in an ensemble of comparators. And of course, our gerrymandering score metric adds to this list. So our gerrymandering score metric was also motivated by the recent court rulings around 2019 regarding maps of Wisconsin, Maryland, and North Carolina. So our takeaway was that courts care about fairness to people and not parties. In the well-known case of Gill versus Whitford, the court ruled that the case was about group political interests and not individual legal rights, and that partisan gerrymandering claims are not really a matter for the court. Justice Kagan added to that that a plaintiff could produce an alternative map comparably consistent with traditional districting principles under which her vote would carry more weight. So guided by Justice Kagan's comment, we were motivated to come up with a metric that would identify voter right disenfranchisement at the smallest granularity possible, which is a VTD, which is the smallest level at which we have voter data. So we look at how a VTD is faring in the map that we are auditing when compared to a randomly generated counterfactual districting called a comparator. So for example, I have here a proposed map with a VTD in purple, where we can see that the VTD is in a district that is 90% blue in the proposed map, whereas it is in a district with only 60% blue in the comparator map to the very right. So we can say that in the original district, the VTD is more packed than it was in the comparator map.
So we consider gerrymandering in terms of cracking and packing. Generally speaking, cracking is the practice of taking a large number of voters who would constitute a majority in one district and then dividing them into several districts where they're less likely to win. And packing is attempting to draw as many voters of the opposing party as possible into one district, thereby decreasing that party's ability to win in neighboring districts. And so because we're concerned with identifying local complaints of gerrymandering, it was important to also formulate what it would mean for voters in a VTD to be cracked or packed. So here we have an example of a toy state with 16 VTDs and 2 parties, one represented by the solid red, the other by the speckled blue. For simplicity here, each VTD only contains voters from one party, and the number of voters in each VTD is labeled. We have an original districting on the left and a comparator on the right. Here, if we look at the central blue VTD with 4 voters, we can say that these 4 voters are cracked relative to the comparator on the right because they received blue representation in the comparator, but not in the original districting. For an example of packing, we can look at this new original districting on the left and a new comparator on the right. If we look at the top left red VTD with 1 voter, we can say that the red voters in this VTD is packed relative to the comparator on the right, because in both districtings, the red VTD is located in a district in which red wins, but the win of the comparator is achieved with a much lower margin of victory. So kind of with these definitions in mind, our question then becomes, how do we evaluate the magnitude of a justified complaint? So providing a single comparator isn't necessarily very compelling evidence on its own that voters in a VTD have been cracked or packed. So with this in mind, our basic idea was to count the fraction of comparators that demonstrate cracking or packing for voters in a VTD. The more comparators a voter can say they're cracked or packed against, then the stronger their complaint. In practice, we use a sample of all valid comparators F, though for this toy state, we were able to list all possible districtings. So with this in mind, we can create a gerrymandering score for a VTD compared to a set F, or for an overall districting compared to F. So for a VTD, its gerrymandering score relative to comparator is the total number of cracked or packed voters in that VTD relative to that comparator. The final gerrymandering score for a VTD is just the average of the gerrymandering score against each comparator, and then the overall gerrymandering score of a whole districting is the sum of the gerrymandering scores for each VTD. So note that our gerrymandering score for a districting is logically unrelated to metrics of partisan proportionality or the efficiency gap. That is, you could have a proportional map that is highly gerrymandered locally, or a not very locally gerrymandered map that's highly non-proportional. So what's helpful about our metric is that because our overall gerrymandering score for a districting is derived from local VTD level gerrymandering scores, we can still identify at a local level how gerrymandering impacts certain people in certain areas more than others. So for example, here, this shows the gerrymandering score by capita of each VTD in North Carolina based on its 2016 congressional districting. The darker green shows regions of the state experiencing more severe gerrymandering. So let's say you're auditing a proposed districting map and you find a very high gerrymandering score. If you present this gerrymandering score as a critique of the districting map, somebody can respond by saying, hey, maybe this gerrymandering score is a necessary result of the spatial distribution of voters in this state. So to evaluate this defense of the map, we generate what we call a witness map. This witness map is not intended as an alternative kind of better districting that we think should be implemented in place of the original map. Instead, this witness is just a valid map based on whatever conditions for validity we choose to use. If we can find a witness with a lower gerrymandering score, then the lower the score, the stronger the evidence we have that the gerrymandering in the original map wasn't actually necessary. So on the slide on the left, we have an example of the 2016 map with its gerrymandering score, and on the right, a generated witness with its gerrymandering score. To generate a witness, we developed a simulated annealing algorithm that works by making small, gradual changes to the original map. So what we've outlined here on the slide is a broad framework and overview for how our algorithm works. I'd like to point out that in step 2, we specified specific global constraints that we implemented in the code base of our paper. However, we're not committed to any specific set of constraints for what would constitute a valid districting. Given any set of constraints, we can still use this method to check for witnesses.
Now, diving into the empirical analysis on North Carolina, first of all, we just initially calculated the overall gerrymandering score of 4 different districting plans for North Carolina. The official map used in the 2012 election, the official map used in the 2016 election, the map generated using the divide and conquer redistricting algorithm developed by Levin and Friedler, which we call the ACR map, and then a map drawn by a bipartisan panel of 10 retired North Carolina judges, which we denote as the judges map. Our gerrymandering score, in some sense, captures a fairness of each map. And so, as you can see in the table above, the 2012 map has the highest gerrymandering score by far, at about 1.5 million, which makes sense since it was explicitly struck down for racial gerrymandering in the court case Cooper v. Harris. On the other hand, the judges in the ACR map, which do not take party data into account in the districting process, performed better overall, with lower gerrymandering scores than the 2012 and 2016 maps. Although both the ACR and judges map don't take party data into account, the judges map can be thought of as a bipartisan gold standard since it's drafted by experts from both parties, and thus our metric is able to capture this by showing a better balance of the gerrymandering score between Democrats and Republicans. On the other hand, the ACR map is simply nonpartisan, so although it's able to achieve the lowest score among all four maps, it is less balanced by party, with Republicans being substantially more gerrymandered than Democrats. Now, to analyze the effects of our witness generation algorithm, our simulated annealing algorithm, we introduced the idea of a heat map. Essentially, we can shade each VTD with color based on what % of the time it's cracked or packed, thus creating a heat map. Darker regions will be cracked or packed in a greater percentage of the comparators than in lighter VTDs. And so this local approach allows us to identify regions of voters that have been impacted by cracking or packing. The top row of figures shows the heat map on the 2016 map. The left side is for Democrats, and the right side is for Republicans. Purple demonstrates that voters have been packed, while orange demonstrates that voters have been cracked. One can see how Democratic voters in the Charlotte and Raleigh metro areas are heavily packed in the 2016 map, while Democratic voters in Greensboro and suburban areas of Raleigh have been heavily cracked. Meanwhile, we ran our witness algorithm in the 2016 map, and in one of our best runs, we got a gerrymandering score of 570,000, an almost 50% reduction from the original score of 1.1 million. The bottom set of figures shows our heat maps for our witness. We see that in the left map, which refers to packing and cracking for Democrats. Democrats are much less packed and cracking is reduced, although there is still some in suburban areas. Meanwhile, on the right for Republicans, we see that packing of Republicans has decreased in far western North Carolina, but cracking has increased slightly for Republicans in the Charlotte and Raleigh areas, as demonstrated by the increased orange colors around those areas. So in conclusion, in this work, we created an interpretable localized score for gerrymandering. And we designed a simulated annealing algorithm to audit districtings for gerrymandering. This audit demonstrated substantial levels of partisan gerrymandering in the 2016 North Carolina map. Further work consists of 3 parts. First, we hope that others can use this approach to audit other states' districtings. Second, we hope people can explore the algorithmic question of designing a method to compute a map with the minimum gerrymandering score. And third, we hope that in the policy and law sphere, this can spur the development of a justiciable standard for partisan gerrymandering court cases, like what the justices described they wanted in Gill v. Whitford. Thank you for listening to our presentation today.